Hello, today I'll be talking about my final project, which was comparing numerical and machine learning approaches for modeling the Van der Pol oscillator, specifically in regards to the forced and unforced oscillator and extrapolating past a training interval with various methods. So what is the Van der Pol oscillator? The Van der Pol oscillator is a non-conservative, non-linear oscillator that is represented by a second-order ordinary differential equation, which you can see on screen. The forced Van der Pol oscillator is a variant of this oscillator with an external forcing mechanism dependent on time, which makes this a second-order non-autonomous ordinary differential equation. Why does it matter? The Van der Pol oscillator and its variants commonly show up in many real-world applications, including RLC electrical circuits, biological oscillators such as certain vocal cords, and neuron activation models. The Fitzhugh-Nagumo model is a variant of the Van der Pol oscillator, and certain other nonlinear systems. And one of its key challenges is that it lacks an analytical solution, especially in regards to the forced Van der Pol oscillator, which means that we have to use various methods to attempt to approximate or solve this oscillator. Which brings me to the first of such methods, numerical methods. We can write the Van der Pol oscillator as a system of first-order ordinary differential equations, and as such, we can use certain numerical solvers to attempt to find solutions. I ended up using two methods in my project. The Euler method, which is a first order method, very fast and straightforward, not known for its accuracy, and the second method, which is the fourth order Runge-Kutta method, also known as RK4, slower but generally more stable. And I ended up calculating this for the time interval from 0 to 20 seconds with a step size of 0.025 seconds, as in the delta t variable. And I compared it to the RK4 method with a fifth of that delta t. However, in certain cases, we don't know the coefficients of our differential equation or the underlying differential equations or physical equations at all, or we wish not to have to evaluate a large number of time steps to find a trajectory value at a point in time, which is something that numerical methods like the Euler or RK4 method fall short in. As such, I ended up training 3 machine learning based approaches to solve the unforced and forced Van der Pol oscillator. A traditional feed-forward neural network, a neural ordinary differential equation, and a physics-informed neural network. These models were trained on data generated using an RK4 solver with added Gaussian noise centered with a standard deviation of 0.1. The system parameters were the coefficient mu equal to 2 on a time interval, again the same as the numerical method, from 0 to 20, with an initial condition of x equals 1 and y equals 0. Starting with the simplest of my machine learning methods, the traditional artificial neural network, where I just trained a feed-forward neural network to predict the trajectory at a given point of time and used auto-differentiation to solve for the y variable in my system, which had the advantage of computational efficiency, being easy to train, and only requiring sampled trajectory data points from my numerical solver. Its disadvantages included that it had no understanding of physics and that it could diverge outside of its training horizon. This was a network with 3 hidden layers of width 128 neurons, and it was trained for 2,000 epochs with a learning rate of 5 times 10 to the negative 4. Which then brings me to my second machine learning based method, the neural ordinary differential equation, which is a continuous model that attempts to learn the vector field that represents a differential equation. It has the advantage of being more stable over long time trajectories and learning the actual differential equation instead of just a function. Its disadvantages include that it requires an ODE solver during training, which I end up using the forward Euler method, which not known for its preciseness, but made sense in this situation due to the computational complexity of training a neural ODE. And it still lacks any physics-based constraints or physically meaningful constraints, relying solely on the data points. Which then brings me to my third method that I attempted, the physics-informed neural network, which is essentially identical to training a traditional neural network, but it uses the differential equations of the system or physics-based principles as a part of its loss calculation and attempts to enforce these on the model. And its advantages include that it requires less or even no trajectory data points, although I gave mine the same number as the other two methods. It enforces consistency with physics in the neural network results, and it produces results tied to our van der Pol oscillator differential equations. Its disadvantages include that it requires the underlying differential equation, and training can be slow and sensitive to hyperparameters, which is why, after much tuning and adjustment, I trained this for 2,000 epochs with the same learning rate as my artificial neural network. Interestingly, the neural ODE required more than twice the number of epochs as the other two methods, at 5,000 epochs with the same learning rate. Which brings me to my results. As for the numerical methods, I found that the explicit Euler method error is visually noticeable compared to the RK4 method in the forced van der Pol oscillator in both trajectory and phase space. You can see those plots have three lines, RK4 with the time step I previously mentioned, the Euler with that same time step, and a quote-unquote ground truth RK4 with a fifth of the time step in the same interval. And as for the unforced van der Pol oscillator, holding all of the other parameters equal, this difference is still present but less noticeable. Which brings me to my machine learning methods. And using the previously mentioned noisy data collected from the RK4 method, I trained these three methods and I got this result where all methods were capable of learning the oscillator reasonably well on the training interval, with the neural ODE doing the worst of all. But past that, only the neural ODE could still attempt to model the trajectory, the other two collapsing to zero, essentially, despite the various coallocation point methods I end up using. For the forced van der Pol oscillator, the results are similar but even worse, including for the neural ODE, in part, I suspect, due to the non-autonomous forcing introducing additional complexity into the attempts to model this equation. And as you can see from both of these slides, the phase space for these is a lot more inaccurate compared to the trajectory modeling, despite the fact that neither of these are particularly excellent. As such, in conclusion, while machine learning approaches are useful for modeling ODE systems and can succeed on known intervals, as in our case, they struggle with extrapolation past those time intervals. Despite the fact that my physics-informed neural network had access to coallocation points from time 0 to 100 or even 0 to 1,000, and despite the neural ODE being designed to be usable over long trajectories. In this regard, numerical methods remain much more reliable for accurate trajectory prediction. Generally, the neural ODEs perform the best at extrapolation, but if you know your interval, pins were the most accurate. Neural ODEs also benefit from short time steps and possibly a more accurate numerical method, which I unfortunately was unable to test due to computational constraints. But for anyone else attempting to model the van der Pol oscillator, I would suggest the RK4 method for your neural ODE and maybe a time step lower than a quarter of a tenth of a second. However, both methods have their uses, and the van der Pol oscillator is far from an unmodelable system, but caution must be exercised in model assumptions and extrapolation attempts. In addition, these machine learning approaches are more designed for situations in which you do not know the exact underlying equation, with the exception of the pin, whereas the numerical methods assume perfect knowledge of your differential equations. Thank you.